Now, what if we want to use the integration to find the area under the curve? Integration is well known as an straightforward or an easier way to find the area under a certain curve for a certain function. Now you have the Cartesian here, you have the y-axis and the x-axis. You have a curve that's called f of x. That function f of x looks like this on the Cartesian, and you have points on the x-axis a and points b. Now if you want to find the area under the whole curve, then you take the integration from a to b of the function f of x dx. Then you already find the area under the curve by solving that integration. But what if you want to find a certain area or a certain segment of the area under the curve, in this case dx? So dx represents a thin stripe along the area under the curve. You can see here f of x represents the whole curve. Dx is that little infinitesimal section or a very tiny little section on the curve. Now going back to our side lamp example, we have the function a of h. In this case, we have on the y-axis square inches, on the x-axis we have the height in inches. Now if we want to find the volume of this lamp, so you have here the height of the lamp going from 0 to 15 inches, and you have the area of the lamp as a function a of h being represented in the curve. Now the volume of the lamp equals the cross-sectional area multiplied by the thickness. So the cross-sectional area is the a of h, which represents as a curve over here, and the thickness is the dh. How thick is that segment of that lamp? Adding all those segments under the curve will give you the area or the volume, in this case, of the lamp base. So V, or the volume, equals the integration from 0 inches into 15 inches as a height. So we're going from 0 to 15 of A of h, which is the area as it is going upward, multiplied by that infinitesimal section d of h. If we let y equals function f of x, which makes sense, that function is continuous and it is positive, it's not negative. And f of x greater or equal to 0, that over an interval of a and b is a definite integral. So definite integral is the limit as n approaches to infinity, which is equal to the delta x approaches to 0, of the Riemann sum of the areas of rectangles under the graph of the function y equal f of x over the interval a and b. So the exact area equals the limit of delta of x approaches to 0 as the summation of Riemann from I equal 1 to n f of xi multiplied by delta x. That would be simply represented as the integration from a to b of f of x dx. That would be the definite integral. So when we say definite integral, that's an integration with borders on top and bottom. That's an integration with limits. You are doing integration at a certain point and ending at a certain point. Whatever in between those 2 points under the curve can be integrated, or whatever function between those 2 points can be integrated and having a final solution. Now let's have f, any continuous function. Then we can identify the definite integration over here in a more simpler form. The f of x dx. So we have the integration from a to b of f of x dx equals f of b minus f of a. So you substitute the top limit into f of x instead of x, minus substitute the a into x as f of a. So we have f of b minus f of a. So we always have the minus between the upper limit and the lower limit. It's like you are taking the difference between the top and the bottom, like in the example of the lamp, in order to find the area under the curve or the integration of that specific function between those 2 points. Let's take an example. We have the integration from a to b of x squared dx. We can say it is b. So the x squared integration would equal 1 over 3 x cubed. Now replacing that with b and a, that would be x cubed over 3 for the b minus x cube over 3 for the a. That would be b cube over 3 minus a cube over 3. Let's simplify it for you. So you have here the integration from a to b of x squared dx would be, that's 1 over 2 plus 1, that's 1 over 3, x to the power of 2 plus 1, x to the power of 3 from a to b. Then that would be 1 over 3, replace the b, instead of the x would be b cube minus 1 over 3 a cube, which been simplified by the author of b cube over 3 minus a cube over 3. So without confusing yourself, firstly you solve the integration without replacing the boundary values, then you plug in the boundary values and get your final answer as needed. Now let's have a more visual example. Determine the value of the integration from 0 to 2 of 3x plus 2 dx. Firstly, we find the integration as an indefinite integral. Assume there's no boundaries, then plug in the boundaries, if that makes sense. So 3x plus 2 would be equal to, here 3x plus 2 would equal to 3 over 2 x squared plus 2x from 0 to 2. That applies on both functions. When you plug in 2 first, then minus when you plug in the 0 instead of x. So 3 over 2 by 2 squared plus 2 by 2 . So 3 over 2 multiplied by 2 squared plus 2 multiplied by, instead of x, 2, minus 3 over 2 by 0 plus 2 by 0. The whole term over here would be 0, of course. So the final answer would be 3 over 2 multiplied by 4, that's 6, plus 2 by 2 is 4, then the final answer would be 10. Simple as that. We got it here as 10. If you want to look at visuals, so you have the function f of x equal 3x plus 2. If you draw that on a Cartesian, that's how it look like. Now you are having the integration from the point 0 and 2 and the point 2 and 8, because you're talking about 0 to 2 on the x-axis. So we are defining from 0 to 2 on the x-axis, but the points would be in terms of x and y-axis. You can find the y in here by plugging into the function f of x. And that's it. You found by the integration the area under the curve, that's in orange in this case. Now if we take the definite integral rules, there's a specific rules that are applied into the definite integral, which is the integration with boundaries. So the integration from a to a of f of x dx equals 0. If you have the boundaries going around the same point, then there is no curve. You are just representing a line, so the integration would be 0. The integration from b to a f of x dx would be minus the integration from a to b f of x dx. There is some authors or some instructors would give you a question with a flip boundaries. If you need to flip those boundaries back in order to make your solution easier for some reason, then just put a minus, then you can flip the boundaries top and bottom as needed with keeping the function as it is. The integration from a to b f of x dx equals the integration from a to c f of x dx plus the integration from c to b f of x dx. So you can create a point in between the two boundaries in order to split this integration into two smaller integration that are in the same area. If the integration from a to b of a constant k f of x dx, you can kick out the constant as we said before. From a, the integration from a to b of f of x dx will be multiplied by the constant k or c or whatever you use. The integration from a to b, as these functions added or subtracted, you can distribute the integration as we mentioned earlier. Same thing as what we did in the indefinite integrals, but it's good here to mention that with the boundary constants for the integration.